Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future today. What does it actually take to train a math reasoning model that can think for 100,000 tokens without burning an absurd amount of compute? That's exactly what Nemotron-Math is about. Here's the core problem. Most math reasoning datasets today are narrow. They come from one reasoning style, one depth, one tone. They also skew heavily toward competition math. That's great for benchmarks, but not great for robustness or long context reasoning. And once you move to 64K or 128K context, training becomes painfully inefficient. Nemotron-Math tackles this by changing how supervision is created. Instead of a single chain of thought style, it uses a very strong teacher model, GPT-OS 120B. For each math problem, the teacher generates solutions in three modes: low reasoning, short and heuristic; medium reasoning, more structured; high reasoning, extremely detailed long form traces. Each of those is generated twice, once as pure text and once with Python tool integrated reasoning. So the model doesn't just see answers, it sees verification, computation, and correction behavior. After that, they filter aggressively. Easy problems get removed. Incorrect solutions are dropped. What's left is 7.5 million verified reasoning traces, some stretching all the way to 128K tokens. The problem sources matter too. They combine AoPS, which gives clean competition style math with StackExchange math questions, which are messier, more linguistic, and more realistic. That mix turns out to be critical. Models trained with both sources generalize better, especially on open ended benchmarks like HLE math, without losing performance on Olympiad style tasks. Now comes the training challenge. Training everything directly at 128K context is wasteful. Most samples are much shorter. So they use sequential bucketed training. You train in stages, first with a 16K context, then 32K, then 64K, and finally 128K. Each stage uses hardware parallelism tuned for that length. Only the final stage pays the full long context cost. In practice, this gives a 2 to 3 times speed up. There is an important pitfall here. At very long contexts, only high reasoning samples tend to exist. If you're not careful, your model collapses into always producing extremely long answers. Their fix is simple but crucial. They intentionally mix some medium and low reasoning samples into the final long context stage. Practical tip: always monitor reasoning mode balance when scaling context. The result is impressive. Both 8B and 30B models converge similarly. With Python tools enabled, they reach perfect majority vote accuracy on AIM. The bigger question now is, can this multi-mode, long context supervision work beyond math? If you found this helpful, hit like, subscribe, and comment which agent system you want to build next. Stay sparked. See you in the next video.